So I'm going to finally wrap up the discussion on object-sensitive analysis, object-sensitive pointer analysis by formalizing the rules for the transfer functions when we're doing object-sensitive analysis. The rules are very similar to all the other pointer analyses that we've seen, for example, context-sensitive pointer analysis. And I'm using Anderson's analysis where we're tracking all the points to set, the set of abstract objects that another abstract object may point to. But the only difference is basically in the way we track the context across function calls and across allocation statements. So my first rule here is that if under an object context C, I am transferring across an allocation statement of the form P equals new something, and the allocation site is L, then recall that we would just say that, P in context C, the point could point to L in context C, and that was how we would tackle it in call context sensitive analysis. In object sensitive analysis, because we are only keeping an object context of one, and the context itself is determined by the allocation site in the allocation site abstraction. So we just say that the points to set of P in context C, written P subscript C with these square brackets, is so that this is the point. This represents the points to set of P in context C that must include this allocation site L. And the important thing to note here is that I'm using the allocation site L and not L subscript C because L subscript C would keep track of two allocation sites. C itself is an allocation site and L is also an allocation site. But in object sensitive analysis, we are, with depth 1, we are only keeping track of single allocation site. So I'm going to forget C and just keep L. Okay. We're going to generalize this later to a D depth object sensitive analysis, but for now I'm doing a 1 depth object sensitive analysis, and that's why this is L and not LC. Okay. The other important transfer is across a function call dispatch. So let's say that small o is an object of type capital O, and let's say in context C I am transferring across a function call t colon equals o dot foo x. So o is the receiving object, foo is a member function, x is an argument in context C, and then t is the return value. Now, you can generalize this. If there was no return value, then that would be a special case of this. So this is the general form of the rule. And let's say this is the definition of the member function f in the class capital O. So O capital O colon f a equals e, where e is the body of the function and a is the formal argument. And this is part of the program. And let's assume that within the context C, the points to set of O, or O in context C, is some set that it can point to and defined by the allocation sites. So let's say those allocation sites are K1 and K2. So O itself may be pointing to some allocation sites, some abstract objects represented by K1 and K2, which may appear elsewhere in this program. So now the question is, how does across the dispatch the transfer happen from whatever x is pointing to whatever a is pointing to? So how does the transfer happen from the actual argument to the formal argument? How does the transfer happen from O, which is the receiving object, to the this keyword in the context of the callee, which is f? Especially given that O could point to multiple objects, and you can generalize this to any number of objects. I'm just using two abstract objects. So first of all, I'm going to evaluate, or I'm going to transfer this information for A in two different contexts, because it's an object sensitive context sensitive analysis, sensitive analysis. So because O could have pointed to two different K1 and K2, so the callee will be evaluated in both those contexts. So one of those contexts is K1. And so I'm going to say that the formal argument in context K1 will I'm going to apply the copy rule and say that whatever is the copy rule, so this looks like AK1 equals OC or sorry, ak1 equals xc, x is the actual argument, and so the points to set of ak1 can be updated using the points to set of x in context C. Similarly, the points to set of this k1, this is in the Colli's context, which is one of the Colli contexts is k1, can be updated using the receiving object O in the caller's context C. So in other words, the points to set of this k1 is a superset of the points to set of OC. And both these rules are only for a single Colli context k1, but we want to tackle both the contexts because O could have pointed to either of them. And so we have two more rules which are completely identical, just replace k1 with k2. So ak2's points to set is updated using xc, just like ak1's was updated. And similarly, this k2's points to set is updated using oc. And this is the how the updates happen across a points to across a function called dispatch. And finally, I want to say that the body of the function itself can be evaluated in must be evaluated in two different contexts. And to say that, I say k1 E is evaluated in context k1 and E is evaluated in context k2, so that all the rules that we all the transfers that we do within E are done both in the context of k1 and in the context of k2. Recall that the more contexts we do this in, the less precision we have, or the more edges we add to our points to graph. Okay. Similarly, if I talk about function return, so let's say inside the body E, there was a return statement that was getting evaluated in context K. In the previous slide, we saw how K could be either K1 or K2. And K was, K must be part of the points to set of OC as we saw last time. So, for example, K1 or K2 as it was in the previous slide. So if I'm evaluating the return statement in some context K, then the value B in this context K will be used to update the value T in the context C. In other words, TC points to set should be updated using BK's points to set. Said differently, the points to set of TC should be a superset of the points to set of BK. Once again, K is a context in which the body of F was evaluated, which is defined by the context, which is one of the abstract objects that OC could have pointed to during the function called dispatch. Okay, so this is on the return path. I'm executing the copy statement from the returned value B to the register T in the caller, where the returned value is getting stored in the caller. And I'm applying the copy rule to basically update them T in its context using B in B's context. And this will be done for each of the Colli contexts. So if there were two Colli contexts K1 and K2, then TC will be updated using both BK1 and BK2, the points to sets. Okay, let's use an example to concretize this. So let's say this is an example of a list class, capital class L, which has this function called append, which just appends a key to the list. So if k equals 0, then it doesn't append, else it allocates a new node of type L. Let's say it has a next point field, so it says this dot next equals n, the newly allocated object, and n dot append k minus 1. So this is it's going to basically append k different nodes to so append k is going to append k different nodes. So it's a recursive call. If k was 0, then it just returns. If it was non-zero, it was greater than 0, then I'm assuming this is greater than 0. Maybe I should have this example should have been something like this. So if it is greater than 0, then I append one node, and then to it I append k minus 1 nodes. Right? And in the main function, let's say I allocate a new list L, and then I call L dot append 10. That's going to append 10 different nodes to L. Okay, so now let's say I run my object-sensitive points to analysis on this this program. The first thing to do here is to identify all the allocation sites. So the allocation sites are A1 in the main function and A2 in the append function. Also, it's important to identify the call sites. So that's C1 here and the recursive call C2 here. Now I start transferring. So I first transfer across the first statement in main, which is L equals new L. And so I say L in context of main, and then let's say the context of main is 0. So L0 can point to an abstract object allocated at A1. So L0 can point to A1. This is the allocation site abstraction. Then I call L.append 10. So whatever L was the receiving object, that is now becoming this object in append, and the context in which append is called is the object of L. So L itself was A1. So the context in which append is called is A1. This variable in the append function. So this superscript append means this variable in the append function. So this append in context A1 points to whatever L was pointing to, and L was recall whatever L in context main was pointing to, or L0 was pointing to, and that recall was pointing to A1. So the points to graph looks something like this. Okay. Now we transfer across if k equals 0. That's not going to do much. We transfer across return. It's not returning a value, so that's not going to do much. But let's look at this transfer function here. So when I look at n equals new capital L, that basically I'm evaluating the append function in the context of L, which is actually A1, because L could point to A1. So I'm evaluating n equals new L in context A1. So I say n subscript A1, which is the context in which n is being evaluated, is pointing to an abstract object allocated at A2. So this is the new edge that I draw with these nodes in my points to graph, because by virtue of this statement. Now next I'm going to transfer along this dot next equals n. So this in context A1, this append of in context A1, which is this dot next. So whatever this is pointing to, that's A1, will start pointing to whatever n is pointing to, which is A2. In other words, A1 will start pointing to whatever n is pointing to, which is A2. So I'll draw an edge from A1 to A2. So by virtue of this dot next equals n, and assuming field insensitive analysis, I draw an edge from A1 to A2 by transferring across this statement. Now, continuing this, I need to transfer across this next call site, which is n.append k minus 1. Now in n.append k minus 1, I'm sorry for this syntax. I mean, this could have been dot, or I'm kind of abusing syntax a little bit where I'm using arrow and dot interchangeably all through, doesn't matter. So append is being called this time in the context of n, and n is pointing to A2. So append will now be called under the context A2. So I say this append A2 will point to whatever n is pointing to, so that's going to point to A2 by virtue of this dispatch from C2 to itself, the recursive call. And once again, I'm going to transfer across if k equals 0, that's not going to do much. Transfer across return, that's not going to do much. And now I transfer across A2 again, but this time A2 is being evaluated in the context A2. But recall, I mean, when we do this, then I'm going to say NA2 points to the allocation site A2. Recall that we forget the context when we see an allocation site in object sensitive analysis. I don't say A2 subscript A2, I just say A2 when I'm doing a one depth object sensitive analysis. So because n was being evaluated in context A2, so I have a new quantity here, NA2, that can point to A2. And because of this dot next equals n, because this append A2 could point to A2 and NA2 is also pointing to A2, I draw an edge from A2 to itself. So because of this dot next equals n, I draw this cyclical edge from A2 to itself. And this is the, I claim this is the fixed point solution for the points to graph. You can check this for yourself. And so this is my final result. We saw this in the previous slide, but written more neatly, it looks something like this. L0, where L0 represents the L variable in the main function, can point to A1, an object allocated at A1. And an object allocated at A1 can point to an object allocated at A2, and an object allocated at A2 may point to another object allocated at A2. And this points to graphs also kind of seems to imply that it can also point to itself, which is actually not true, but that's the imprecision we get in this points to analysis. And then there are all these other variables in their respective contexts and where they can point to. And that information is also encoded here, written more neatly in this figure. Now, I just want to finally wrap up the discussion by saying that so far we are considering a one-depth object-sensitive analysis. It's easy to generalize this to a D-depth object-sensitive analysis, where instead of saying that I'm going to update the points to set, when I see an allocation statement, I'm not going to update the points to set of PC using L, but I'm going to have this operator called, let's say, concatenate with D bound. So let me put this as this plus, circled plus underscore D, such that depending on D, it's going to take only the most recent, the top top D allocation site. So for example, L1, L2, L3, LD, concatenated with LD plus 1 is just going to give me L2 dot 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 LD plus 1. So I'm going to just forget the L1. And if I concatenate, if my concatenation was with a smaller string, so L1 dot dot LE where E is less than D, then I'm going to keep all of them. So it's easy to see that if I put D equals 1, I get exactly what I had in my previous rules. But if I use D equals 2 or 3, then I can actually tolerate bigger strings, and everything else remains the same. So the only thing that changes here is what happens across an allocation site, because now we keep track of this object was allocated at this allocation site in the context of an object that was allocated at that allocation site. So that would be a two-depth object-sensitive analysis, and that's what this rule implies.